Hello and welcome to speed control of a DC motor. This is the setup that we have built up. This is the motor that we have, and this is the encoder, and this is our sensor. And on this mount, this is the ideal position that has been set, and this can be also adjusted over here with the help of this nut. This can be loosened and the sensor can be brought near or farther away from the fan as required. And here we have the entire circuit. We are actually using two boards. This is the master board, this is NX1000, and this is the slave board, BOE. This is only used for the purpose of providing PWM. And let's move on to the GUI in MATLAB. We are using asynchronous communication with the computer. As you can see, this is a USB cord connecting by the RS-232 line. Yeah, that's all for the setup.
So here is our MATLAB GUI. First of all, we will move on to the diagnostics parts. By the way, I will just tell you that we have the calibration here, we have the controls here, required RPM can be fed here, and the system can be run or stopped from these radio buttons. Moving on to the diagnostics, I will hit this diagnostics button. Now what will happen, the system will attain its maximum RPM and it will try to judge whether the system is healthy or not based on the RPM count. So as you can see, the RPM count registered is 65 and the corresponding maximum registered RPM is 4875. So the system is in healthy state. This can be used basically to debug the system in case there is any error. Now moving to the calibration part, we have three levels of accuracy here. We have the high, the medium and the low. So we'll first try with the high accuracy. Basically, the higher the accuracy, the more the time that is taken to calibrate the system. And so if I hit the calibrate button, the system will first attain its maximum RPM. It will stabilize at that RPM and then it will try to reduce the duty cycle and the corresponding optical encoder count will reduce. So we have finally an equation from the optical encoder count to the duty cycle, which can be used for open loop as well as other different kind of controls. So as you can see, the duty cycle is varying and the optical encoder count is reducing. The system basically is showing a second order second degree polynomial kind of response. So we finally fit a second order polynomial in this. You can see the root mean square error here, the coefficient of determination and the duty cycle equation. Based on these statistics, it will also recommend whether the calibration is good or poor. So you can just check it right away, and based on this feedback message, you can either use the default calibration or you can go with the current calibration. I will just quickly show you how to do it with low. So we'll select low and you can see the curve fitting or the curve obtained will not be that accurate in this case. So basically we are reducing the duty cycle by larger steps in this case, and so you can see the root mean square is a bit more, but still it's kind of good, so it's showing the good calibration. So using the default calibration, we will first move on to the open loop control. The required RPM is set to 2000 and we will hit run. So we have now the two plots. One is the RPM plot, another is the RPM error plot. So you can see in case of open loop control, though we have a stable RPM, but there is quite a lot of steady state error in the system, and so the open loop control is not that good in industrial control. I will stop the system. Now moving on to the on-off type of control, I'll hit the on-off control run button. So you can see there are a lot of fluctuations in on-off control, though it is able to track the signal, but you see a lot of fluctuations and oscillations in the steady state as well. So I'll just hit the stop button. Now moving on to the differential gap, we can also set the gap. Say I will set it to around 500. This is basically the gap at which the switching will take place. I will hit the run button. you can see that sometimes the system fluctuates, and now it's trying to track the signal. So though the RPM gap is mentioned as 500, the switching actually takes place after 500, and that's why there are a lot of oscillations in the response. I'll stop this thing. Now moving on to the P control, I'll just hit the run button again. We can also set the KP, KD and KI values. So you can see there is a steady state error with the proportional control, and since the integral control can only control that thing, so we will have this kind of error in PD control as well. So now moving on to the PD control, hit the run button. So you can see again there are faster response time because of the KD present here, but still we see that there is a error. I'll just hit the stop button again. Moving on to the PID control part, I'll hit again the run button. So in this case, just hit the stop button. So moving on to the PID control, I will set the required RPM, say around 4000, and I will hit the run radio button. So you can see the system is trying to attain the 4000 RPM, and it has some overshoot in the beginning, and then the magnitude of the overshoot is reducing, and the system is trying to track the required RPM. The performance of the system can also be varied by feeding in different gains, KP, KD and KI, based on the requirement. So I will stop the system, and we can also clear the plot if I hit the clear plot button. Here also the data login option is there, so we can log the data, the response of the system. And we also have a video option which can be used to monitor the system, the actual setup, but since the drivers are not working, so the video is not there. The video preview window is through MATLAB, so we have interfaced the webcam through MATLAB, and I will now hit the exit button.
We'll give a short demo of how our system responds to the external physical disturbances. Now here is an IR remote. I'll give the disturbance slightly with this. Is it visible? Yeah, it's slightly it must be visible in the webcam. Okay, now as you can see, I'm giving a slight disturbance, and you will see the corresponding change in the waveform. As you can see, there's a sudden drop in this, but our controller tries to bring it back to the steady state. Now there's another physical disturbance. I'll bring it through a paper. As you can see, there's again a slight disturbance here caused by the paper, but our system comes back to stable mode. Adios.
So you're signing off with speed control of DC motor. This has been an effort of 4 people. Unfortunately, the 4th person can't be here today. So here we have Priyanshu Agarwal, Ravi Kiran Cholangi, and myself, Dipendra, signing off. Yeah.